Since NASA's Juno mission began orbiting Jupiter and sending data back to Earth last July, Juno scientists have all sounded pretty like they are very excited, and very confused. Almost nothing is as we anticipated, Juno's principal investigator Scott Bolton told Wired in May. But it's exciting that Jupiter is so different than we assumed. The data's telling us our ideas are all wrong, says Randy Gladstone, lead investigator of Juno's ultraviolet spectrograph. But that's fun, it's a real mystery, says Barry Mock, lead investigator of Juno's Jupiter Energetic Particle Detector instrument. Yes, they call it JEDI. It's thrilling to be part of this mission. What exactly is so baffling and invigorating about Jupiter? The simple answer is everything. Juno's data has defied conventional scientific wisdom, with everything from the color of its poles to the bizarre fluctuations in its gravity and magnetic field strength. But today in particular, Jupiter's source of scientific wonder is its incredibly powerful auroras, which ceaselessly whirl around the storm-torn gas giant. And they aren't just challenging expectations, they're sticking it to the earthly laws of physics. First, let's lay out how auroras actually work. On Earth, anyway. In Earth's strongest auroras, those polar phenomena you've heard so much about, electrons accelerate along magnetic field lines toward the poles. They form an orderly inverted V structure as they go. Their potential energy is lower on the edges and ramps up into overdrive in the middle over the pole. The part you can actually see is the result of those accelerated electrons raining down on Earth's atmosphere, where they bash into oxygen and nitrogen molecules. As the excited molecules calm down, they release photons and create an undulating light show. According to Mock, the author of a Jupiter aurora study released today in Nature, it's in that electron acceleration phase that Jovian aurora stop making sense. Mock and his team are seeing monstrous electric potentials over Jupiter's polar regions, anywhere between 10 and 30 times greater than any seen on Earth. Which they expected. Everything's bigger and badder on Jupiter. Trouble is, Jupiter's aurora isn't 10 or even 30 times stronger than Earth's. It's about 100 times stronger. And there is no earthly explanation for that discrepancy. Basically, the aurora is a factor of 10 brighter than it should be based on Earth-like physics, Mock says. That is textbook ripping, whiteboard flipping crazy. It means that whatever process accelerates Jupiter's electrons up to 1,000,000 electron volts is likely a total unknown. And Mock, with the help of theorists and data from a few more orbits, is already on the trail of what that might be. After Orbit 7 we saw what I would consider to be the smoking gun, Mock says. Mock's JEDI instrument saw the characteristic inverted V structure, but the electron excitement didn't end there. As the electrical potential rose at the peak of the V, the acceleration went from coherent and linear to random. Mock calls that a stochastic acceleration process. Something goes unstable, and you start forming these waves, Mock says. Some electrons gain a lot of energy, some just a little. What makes things get all unstable and random? Unclear. Though, stepping deep into the realm of speculation, some theorists have suggested it could be electromagnetic plasma waves churned up by the turbulence of Jupiter's magnetosphere. But while the mystery of Jupiter's super-strong auroras just keeps getting murkier, the reason for studying them is perfectly clear to Mock. We're trying to understand how physical processes in the universe behave, he says. And ain't that what science is all about?